Sun from Tsinghua University.
Hello everyone, my name is from NTHU, and today I'm going to show you my work using JWST to explore the earliest universe in mid-infra. So let me first start with the history of the universe. In fact, particularly is the infra star formation history. So for now, we only know the evolution as the luminosity function to ratio to 3.6. But how about the higher ratio other than 3 to 4 or 5? We never know. So in this work, we use JWST to explore this circle region. But how to do it? We use the luminosity functions. So you may come up with a question that what is the luminosity function? The concept is very simple. So when we talk about we build a luminosity function, it's actually we count the galaxy's numbers in a certain value in a certain brightness and a certain time, as this plot shows. So when we use mid-infrared, actually the dusty star formation is a very important part in the evolution of the universe. But most of them are obscured because of dust, and we cannot use the OV, optical or UV telescope to observe them. Instead, astronomers use the mid-infrared. So as you see, the light from the young star is mainly in UV or optical, so we can build a UV luminosity function. But this is not comprehensive for understanding the history of the star formation activity. So when the dust will emit those light in mid-infrared, we cannot thus build the infrared luminosity function. In this work, we use the power of the JWST. So you can see in this comparison of the mirror size of each. In left side is the previous generation space telescope in infrared, and left is just a JWST you are familiar with. So with this 6.5 meters mirror, we can significantly improve the resolution of the image in infrared, like this shows. And our previous work also suggests the JWST could have the ability to explore the sources in microgram speed levels. So there are two ways to build a luminosity function. One is the model approach. You can, if you are interested, you can see the poster 78. But this method requires many assumptions in models like galaxy conversion or local luminosity function or evolution parameters. But in this work I'm presenting now, we only use the image data from JWST, which do not need any model assumption or other things. So the data we use is the JWST CS field survey combination with the EGS catalog. The CS data we use including 4 mirror points which have a square coverage in 6 filters from 7.7 micron to 21 micron. And we apply the source extraction and 80% completeness from this our work to get the photometry of those mid-infrared sources. And this figure just shows the sky curvature of the CS survey. In EGS catalog, it contains optical and near-infrared data from Hubble and CFHT error. And we use those catalog photometry to match the source in our catalog. So in total, we have around 600 sources with 21 photometric bands. And we use the SED fitting software Seagull to obtain the photo C and the spectrum of our gaseous samples. And we use this parameter and remove the band fit with reduced category larger than 5. And this is just a simple plan of our SED. Then for the photo C, we obtain, I just wrote the distribution of our gaseous sample, and we divide them into 4 ratio beams as this value shows. Then we apply analysis first the K correction to correct the photometry for each filter we use. Then we use this 1 over the mass method to build the luminosity function. As this equation below shows, it's just a mathematical way to explain how we build this histogram or distribution. So let me go to my result. This is the luminosity function before our work. So I plot the literature luminosity function from Akari or Pfizer, and you can see the lowest luminosity they can give goes is like this value, 10 to the 9 or 10 to the 10.5. But with JWST, we can go to the 1 to 2 order factor gases. In each ratio beam, you can see the change. And most importantly, we also have a luminosity function for ratio beam 3 to 5.5. And we cannot see this before. Our luminosity function is very well connected with previous work. And in this yellow green region, you can see a very clear density evolution and luminosity evolution from ratio 5 to 1. But the luminosity function I just showed contains all of the population of gases. So what about different populations? Here we divide the gases into star-forming gases and AGN with its AGN luminosity fraction at 20% as criteria. And you can see the star-forming gases luminosity function actually follows the trend of the luminosity function of all gas combination. And star-forming gas is actually the majority even at ratio larger than 2. This is not can see before because previously the high ratio luminosity is dominated by AGN. But in our work, the AGN is only dominated at the highest ratio and the brighter end, which is 3 to 5.5, and is not dominated elsewhere. So by integrating our SED from 8 micron to 1000 micron, we can obtain the total infrared luminosity function. So I just plot the simulations as I just showed, and you also can see the very clear density evolution from 5 to 1. So let's go to the first figures I showed. Here we put the infrared luminosity density to ratio 4.25. And this point, I think is no one has ever seen this before, and this is the contribution from the JWST. And from those 4 data points, we also spot a star formation rate peak at ratio 1.5. So in a summary, here we present the first mean-infrared luminosity from JWST, which is can explore the farthest gases to ratio 5 with the luminosity, solar luminosity 10 to 11, and the faintest end at ratio 0 to 1 with the solar luminosity 10 to 7 in mid-infrared. 3.6, but now we can go to such high early universe with JWST, and this could actually be the first work to show the early universe in mid-infrared. So this is all my writing. Thank you very much.
Questions?
Yes, thank you for the talk. I have 2 questions. The first one is, you mentioned that you remove systems with reduced chi-square higher than 5. I'm just curious, what are those systems?
This is just for you mean I remove this criteria, right?
Yes.
Actually, we don't investigate those gas peaks because we just want to get the gas result from signal. But those gases we remove is very less part of our sample, like 2 to 5%.
Okay. And my second question is about the final omega far infrared. So from the JWST, based on the luminosity function, as far as I can tell, you can only detect the brightest galaxies at redshift 4 and 5, right?
Yes.
So in order to estimate this plot, I guess you need to assume some shape of the luminosity function.
Yes. I didn't put the equation here, but we assume a double power law distribution of the luminosity function, and we fit for this our data point. If you can see dotted line, is our fitting function, and we use this to obtain the omega.
Okay, thank you.
Okay, well, we have time for one more quick question. Okay, no more questions. Let's thank the speaker again. So the next speaker is